Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having lecture number 23 and we will be discussing about sequential analysis, right? So it will be the continuation of the previous lecture and we will be discussing more about analysis regarding the sequential circuitry, right? So before starting, let's have a comparison regarding the analysis in the context of combinational and sequential logic, right? So you can see that over this slide we have the two columns, right? On the left we have the combinational and on right we have the sequential, right? So whenever we are making combinational analysis, right, so we normally come across Boolean equations, right? We draw truth tables, right? And moreover, in a combinational circuit, right, as we know that output is a function of input only, right? And the we have output present there as long as the input is present. As we remove the input, right, we don't have any output, right? So this is the key difference. And on the other side, in sequential analysis or sequential logic, we have state equations, right? We have state tables, state diagrams, right? And output can be a function of input and the current state, right? And we also have next state, which is basically the function of input and current state, right? So this is a sort of comparison when we talk about analysis regarding the combinational and the sequential circuit, right? So we have to keep in mind whenever we are performing analysis, right? Okay, and as we are studying sequential circuit analysis, so we have to go through certain number of steps, right? And first you can follow those steps, right? It depends on the requirement, right, on the problem, and we can follow these steps accordingly, right? For example, we have to obtain state equations, right? And while we are obtaining these state equations, we have to keep in mind the flip-flops, right? And normally the input over the flip-flop is provided by the combinational circuit, right? And the equation we get from this combinational circuit, right, it is normally named as input equation, right? If we have more than one equation, then we have more input equations, right? And sometimes the output, right, it is also composed of combinational logic, right? So we have output equations, right? And then after getting all those equations, we need to fill the state table, right? So we have the input, right? And then we have the possible number of states, right? And after having those equations, we put the values in those equations and we fill the state table, right? So that's why we normally compute all the combinations, possible combinations of inputs and the states, right? That is known as current state, right? And then we fill the next state column in the table, right? And the output, right? And finally we draw the state diagram, right? So these are the steps we have to go through in order to have sequential circuit analysis, right? Okay, and then as we know that we can have a clocked sequential circuit, right? So in order to have the analysis of such clocked circuits, right? So here we have mentioned a state table, right? And then you can see that the state table, right, the columns within the state table, right? So we have the present state and the input, and then next state and the output, right? So this is the state table regarding the clocked sequential circuit, right? And here you can see we have, if we join the present state with the input, right? So you can see a very familiar sort of possible combinations. These are 0, 0, 0, right? Starting from 0, 0, 0, and then 0, 0, 1, and 0, 1, 0, and so on and so forth till we have 1, 1, 1 in the last row, right? So this is 0, 1, 2, 3, 4, 5, 6, and 7. So starting from 0 till 7, right? So these are the possible combinations, right? So as we have mentioned in the number of steps, so this is the state table, and we have placed all the possible combinations of the present state and the input, right? And then you can see in the third column we have the next state, right? And this is the output. So after having the equations, right, we have to put all the values in those equations, and then we will be able to calculate or compute the next state and the output, right? So normally we have the expression for the next state, right? And then we have the expression for the output. If I go back, right? So these are the bullets we have mentioned, right? So we can also represent the same state table, right, in another form, right? So here what we have achieved, you can see that we have reduced the number of rows, right? And we have split the column for the input, right? So here we have a single input, right? So here we have, you can say, two sort of inputs, x is equal to 0 and x is equal to 1, right? So this is the next state for two possible values of the input, x is equal to 0 and x is equal to 1, right? And again here we have splitted the output column, right, for x is equal to 0 and x is equal to 1, right? So, and you can see the number of possible combinations for present state 0, 0, 0, 1, 1, 0, and 1, 1, right? Actually, we have obtained this reduced state table from this, right? So if I look 0, 0 for input 0, 0, 1 for input 0, right? And then 1, 0 for input 0, and then 1, 1 for input 0, right? So you can see that we have x equal to 0, and then 0, 0 for x equal to 1, right? And 0, 1 for 1, right? So these are the present state, and then next state again for 0, x is equal to 0, for next state x is equal to 1, next state for x is equal to, right? So you can see that against that combination, right, whenever we have x equal to 0 and x equal to 1, whatever next state is, we have splitted this column depending upon the value of x, and same we have done over here, right? Right? So if, for example, I have a sequential circuit, right? And in that sequential circuit, I have m number of flip-flops, right? And n number of inputs, right? So I want to calculate the number of rows in order to present, all right, or in order to draw the state table, right? So how I can calculate? So this is a very simple methodology or formula, right? So here, if you have two flip-flops, right, and one input, normally in our examples, for sake of simplicity, we have one flip-flop or one input, or sometimes we have two flip-flops or one input, right? So here we have two flip-flops and one input. So the possible combinations, right, or you can say the possible rows, in other words, then, right? So 2 raised to the power 3 minus 1, right? So as we know that we start counting from 0, whenever we talk about the digital logic design. So we will start from 0 and we will reach till 7, right? You can see here. So total count of 8, right? Because in normal counting you can say 8, right? For from the context of digital logic design, we normally start from 0, right? Right? So these are the equations, right? And here we have the equation for the next state. T plus 1 is mentioning the next state, right? So this A has no bracket or subscript, so it means this is the present state, right? This is the next state, right? And this is the input. So similarly, we have the equation or expression, Boolean expression for output y is equal to a plus b into x, right? Okay, so here there is another methodology, or there is another mechanism to represent the state table, right? That is the state diagram, right? So you can see that we have a circle, and inside the circle we have different values, right? And those values, they represent the states, right? If I go back, this is the present state, right? Here, if I take this table, right, this is also state table, 0 0 0 1 1 0 1 1, right? So here we have 0 0 0 1 1 0 and 1 1, right? And then you can see different arrows, right, and some values which are written over those arrows, right? So if I want to go from this state to this state, so you can see that we only have this arrow, right? So this arrow is mentioning the transition from one state to another state, right? So what is the cost of that transition, right? So for that, right, I have to apply an input of 0 and I will get an output of 1, right? So this numerator, right, is mentioning the input, right, and this denominator is mentioning the output, right? And if you look here, right, so we have an arrow, right, that remains on the same state, right? So it means whenever we apply, right, 1 input, we will get the 0 output and we will have the same state. There will be no change, no next state. We will be having the same state, or you can say present state. We will be sitting at the same state, right? Okay. One of the advantages of this diagram is that they are very easy to plot, right? You can see that we have circles and we have some arrows, and we have some values written over those arrows mentioning the input and the output, right? So it means it's rather easier, right, to represent. Okay. Then there's another important terminology, right, regarding the analysis, sequential circuit analysis, and these are the input functions and the characteristic tables, right? So as I have mentioned in the previous lecture, that in a sequential circuit we have both the logic, combinational logic and sequential logic, right? So we need to know the type of components used for sequential logic, right? And we also need to know the circuitry involved in the sequential logic, right? So as I have mentioned that whenever we talk about the sequential circuitry, right, so we have both sort of logic, combinational logic and sequential logic, right? So for the combinational logic, we need to know the Boolean equation, right, or Boolean function, right? And regarding the sequential logic, we need to know the flip-flop that are being used within that sequential circuit, right? So all that information is necessary or required, right, in order to draw the diagram of a sequential circuit, right? So the combinational circuit, right, that generate the input, right, for the flip-flop, right, and sometimes it is also used in order to have the output, right? For the input, the combinational logic that is providing input to the flip-flop, that are the memory elements, or that are the part of the sequential logic, right? So the combination circuitry present at the input of the flip-flop, right? So as a result of that combinational circuitry, we have the Boolean expression, right, or Boolean equation. So that equation or that expression is called the input function, right? And if you talk about the output, right, so that function or that equation is called the output equation or output function, right? Then obviously we have the circuitry, right? And moreover, you can say that there is a very complicated relationship, right, between the flip-flop and the input, right? So it's not easy to define the relationship between the input combinational circuitry or input combinational logic and the flip-flop. Similarly, the next state, right? So for that, we need another mechanism, right, or another methodology, and that is overcome with the help of characteristic table, right? So here we have the characteristic tables for the sequential logic, right? So here you can see that we have rather than because when we studied different flip-flops, so normally we have a Q and Q bar, right? So Q is the normal output of that flip-flop and Q bar is the inverted, right, output of that flip-flop, right? So here we have some different representation, right? So due to that difference, we call it a characteristic table, right? So you can see here we have t plus 1. So this t plus 1 is mentioning the next state, right? And here we have jk. So these are the combinations, right? So if we have two input jk, right, so we have 4 different combinations. So you can see the next states are, so here no change, it means the flip-flop will remain at its present state, right, or previous state. So and here we have 0, right, this is the next state. Here we have 1, right, so here we have the complement, right? So it means a toggle will occur when we have both j and k 1 1, right? If we have a 0 as a previous state, so next state will be 1, and if we have a 1 as 1 is stored in the flip-flop, we have a 0. So this is the complement, or you can say it or name it a toggle, right? So here we have the D flip-flop again. Here we have T plus 1, right? Again RS flip-flop, right? This is the T flip-flop, right? So these are the characteristic tables for all the flip-flops which we have studied so far, right? So we have studied D flip-flop. So we started from RS, then we studied D, right? After D, we studied JK and T flip-flop, right? So these are the 4 flip-flops, and these are the characteristic tables regarding those flip-flops. And our sequential logic is normally based on those flip-flops, right? Because we need memory elements, right? So here we have the tables, right? And we have the symbolic representation for those flip-flops, right? And in addition to the symbolic representation and their characteristic tables, we have the characteristic equations, right? So you can see we have QT plus 1 is equal to D, right? For JK flip-flop, we have QT plus 1 is equal to JQ plus K bar Q, right? So we have derived. So for T flip-flop, we have T XOR Q, right? So Q is the previous state, right? Or the current state, you can say. If we call QT plus 1 next states, then Q is the present state, right? And let's talk about state table, right, in more details, right? So we have 4 sections: present state, input, next state, and output, right? Or you can say we have 4 columns, right, representing present state, input, next state, and output, right? And if we have a flip-flop, right, or then for example we have a circuitry where we have 2 flip-flops, right? So then we will be having A and B, right? And this depends again on the circuitry. We can have 1 input or we can have more than 1 input. And if we have AB, right, here, so normally we will be having the next state column like this, right? So if you have 3 flip-flops, then there will be a C over here, and similarly we have a C for the next state, right? Okay, and then this is the 2D state table, right? So here we have mentioned the same state table, but here we have splitted, right, this next state into 2, right, for x equal to 0, for x equal to 1, right? And this is the again same, right? So let's start examples, right? So we have to analyze this circuit, right? So here you can see that we have the combinational part that is composed of those gates and OR, right? So here we have AND, OR, NOT, AND, right? And we have 1 input, and this part is the sequential part, right? So here we have used flip-flops that are working or functioning as a memory element, right? So here we have the 2 output from each flip-flop. This is A and this is A bar, right? So this is B and B bar, and this is the clock pulse, right? So we have 1 output, right? So there can be a lot of different questions which we can answer, right, after analyzing this circuit, right? So first you can straight away answer this question. This is a sequential circuit. Why? Right? Because it involves memory elements, right? So we have we can store the state, right? And then obviously we have 1 input, 1 output, right? So that we will answer, you can answer, right? So how many states? If I take A, B, and X, right? So if I go back, right? So present state and then input X, right? So how many possible number of states we can have? So you can straight away answer this question, right? That is 8. And you can always calculate, right, with this, right? If we have 2 flip-flops, right, and 1 input, so that is 3, right? So 2 raised to power 3 minus 1, right? So 7. So if I start counting from 0, so 0 to 7. So these are the possible states, right? If I go back, right, you can see that we have mentioned that, right? And then because we have used D flip-flop over there, so let's have a review of D flip-flop, right? So this is the table, right? Here we have mentioned the characteristic table, right? So you can see that this is the, if I go back, right? So this is the characteristic table, right? Right? And this is the characteristic equation, right? So we have the same review, right? So this is the characteristic table, right? So but here we have a more elaborated characteristic table, right? So you can see the difference, right? So here we have the previous state and this is the next state. This is the previous state and this is the next state, right? So whenever D is 0 and we have present state, you can say, or if I focus on this, then you can say the previous state. So if let's talk about the present state. So if at present 0 is stored, so and we have D at 0 at the input D, so we will have 0, right? And if we have 0 and D1, right? So you can see that we have next state 1, right? And then if we have 0 here and 1 in the presently 1 is stored, so we have a 0 as the next state, right? So 1, 1, we have 1, right? So here we have mentioned the characteristic table differently, right? By considering the present state and the next state. T is present state and T plus 1 is the next state, right? So this is the characteristic equation, right? And this is the symbolic representation. We all know that we have here we have the positive edge, right? And here we have the negative edge trigger due to this bubble, right? And this is the output, and this is the inversion or complement of the output, right? So these are the equations, state equations, right? As we have two flip-flops, right? So the first letter here is mentioning the type of flip-flop, and the second is a unique tag for the flip-flop. So here we have A, right, flip-flop, and here we have the B flip-flop, right? So this is the state equation for this, right? And this is the state equation for this, right? And this is the state equation, right, for the output, right? So y is equal to A plus B x bar, right? And then what we can do, right? So we have to first calculate the possible number of combinations regarding the present state and the input, right? So 0 0 0, right? 0 0 1 0 1 0 and 0 1 1 and so on and so forth, right? So what is the next step, right? So we will put those values in those state equations, right? And we will be getting the next state and the output, right? So for example, if I put A plus B, so I focus here, right? So here, right? So I have to put AB 1 1, right? X 0 and X bar 1, right? So I will be getting Y 1, right? So we will put those combinations one by one, and we will be filling the next state and the output, right? So this is the same story, right? Here we have represented the same state table in another way, right? So you can call it a two-dimensional state table, right? Okay, and then obviously we can draw the state diagram, right? So from this state table, so what we can do, if I talk about this, so here we have the state table, right? So we have four states, right? 0 0 0 1 1 0 1 1, right? So here you can see that, and then we have to whenever we have x equal to 0, right? So I represented those states by cycles, right? So 0 0 0 1 1 0 1 1, right? And then if I have x is equal to 0, input 0, so what will be the next state, right? 0 0. So I will be at the same state and output is 0, right? And then 0 0, right? So you can see that when x is equal to 1, right? So here we have x input 1, right? And you can see the output is again 0, right? And we have to move from 0 0 to 0 1, right? So 0 0 to 0 1, right? That is for x equal to 1, right? So if you talk about this, right, 1 1 from 1 1, right, or you focus here, right, on those states, present states with 1 1. For 1 1 and from 1 1, when we have x equal to 0, right, input is 0, right? So this is the input 0, right? And you can see that we have the output or the next state 0 0 and output is 1, right? So this is 1 and next state is 0 0. So again 1 1, we are sitting at this state, right? And we have applied 1 as input, right? So here we have 0 as input. So this is 1 and output is 0, right? But we have to move from 1 1 to 1 0. So this is the arrow mentioning the transition from 1 1 to 1 0, right? So this is the equivalent state diagram, right? So you can have, you can if you have this state diagram, you can draw the state table, and if you have the state table, you can draw the state diagram, right? Okay, right? So then we have another example, right? So here we have a D flip-flop, single D flip-flop, right? So similar questions we have to answer, right? What is the output, right? So here we have some additional dimension, right? So we have to find the type of machine over here, right? So this is the equation, right? So what sort of equation or type of equation is, right? So this is the state equation, right? So you can see we have the A, only one flip-flop. So A XOR X XOR Y, right? So we have two inputs, right? So this is again something different. That in previous example we have only one input, right? So here we have two inputs, right? And from this state equation, right, what we can do, this is the present state and this is the next state, right? So you can see that we have again the same story, right? Same sort of combinations, right? 0 0 0, 0 0 1, 0 1 0 and 1 1 1, right? And this is the next state, right? Because we have to put those values over there, right, in this state equation, then we can calculate or compute the next state, right? And from this state table, what we can do, we can have the state diagram, right? So here we have 0 and 1, right? Because we have, right, if you talk about this, right, so you can see that we have only two states, 0 and 1, right? And these are the different input combinations, right? So if we have 0 and we have different combinations of input, 0 0, right, 0 1, 1 0, 1 1, right? So this is when we have A 0, or you can say present state is 0, right? And then we have present state 1, then again we have four combinations, 0 0, 0 1, 1 0, 1 1, right? So if we are here at 0 state, right, and we have 0 0, right, we will be at the same state, or we have 1 1, you can say that we have the same, right? And if we have 0 1 or 1 0, so this 0 1 or 1 0, then we have to move to the next state, that is 1, right? Right? So you can see 0 1, 1 0, we move to the next state, that is 1, right? So from 1 1, if we are here, the present state is 1, right, because we have moved from here to here, right, 0 1 1 0, right, and from 1 you can see for 1 we have 0 0, right, and 1 1. So these are the two possibilities, that if we are sitting at 1 and we will remain at the same state, right, so 0 0 for 0 0 and for 1 1, right. In order to move from one state to this state, that is 0, we need 0 1 and 1 0, right. So this is the state diagram, right, and then we have another circuitry, right. Okay, so we will talk about this dimension, that is to distinguish that either this is Moore machine or Mealy machine, right. So here we have another example, right, but here we have different flip-flops, right, J and K, right, and here again we have J and K, right. So again we have to answer these questions regarding the analysis, right. So of course this is the sequential circuit, because this includes those flip-flop that are the memory elements, right, and we have the feedback. So we have one input, right, and how many output, right. So this is again the state, right. So we have two flip-flops, right. So A, B, these are the states, right, and here we have the input X, right. So 2 plus 1 3, 2 raised to power 3 minus 1. So these are the possible number of states or combinations, right. Okay, right. So before analysis, let's have an overview of this JK flip-flop, right. So again we have the characteristic table, right, and this is the characteristic equation. We all know this, right. So this is JK inputs, and this is the next state, and QT is the present state, right. So you can see we have different combinations, right, possible combinations, and then we have next state will be the present state, right. So this is 0, next state will be 0 1, and this is the toggle, right. So this is the characteristic equation, right. So from this circuitry, what we need, right, we first will go for state equations, right, and you can see that we have two flip-flops, right. So we have JA, KA, right, JB and KB, right. So this is JA and this is KA, right, and then we have to make some substitution, right. So here we have A and B, right. So this is because of this feedback, right. So you can see that we have the value, right, for A and B. Okay, right, and then after that what we need, right, after having those values, what we can do. So we all know, or we already have the information regarding the combinations, right, or you can say the states, right. So here we have ABX, right. What we need to do next, right, we will be putting those values, right, in those equations, and then we will be calculating the next state, right. So this is the next state, right, and then how many states we can have, right. So there is one mistake, right, that has been propagated, right. So here you can see that how many number of states we can have, right. So you can correct, right, there is rectification for this mistake which have been done, right, or which has been propagating regarding the number of states, right. So if you go back, so here we can say that these are the possible combinations, right. So possible combinations, they are somewhat different from the number of states, right? So this is you have to be very careful whenever we talk about the states and the possible combinations, right? So then we have to draw the state diagram, right? If I have the state table, right? So this is the state table mentioning the present state, input, and the next state. So if I look at this circuit, so we don't have any output, right? So we have the present state and the next state, right? Present state and the next state, right? So, and we have the input. So you can see that we have only state equations for the next state, right? So here we can see that we have to put the values over there, and then we can populate this next state, right? So for 0 0, right, x0, you can put those values over there, right? So we can calculate, right? So if we put 0 0, right, let me try this combination, right? A1 B0, and we are putting this over there, right? So A1, so we have 0 B0, right, plus A1 B0, so bar will be 1, right? And then we have A1, and what is x0, right? So we will be having 1, right? So you can see we have A1, right? And if you talk about the B, right, so let me write here, B0 is bar is 1, and x is 0, its bar is 1, right? So plus A1 B0 x0, right, plus A bar 0, so all will be 0, so we have 1. So you can see we have 1. So you can put all those different combinations over there, and you can populate the next state table column, right? Right. So we have the answers, right, for all those different queries, right? And then we have another example over there, right? And this is the same story, right? So here we have the only difference is, right, and if I go back, right, so here we have 2 JK flip-flops, right, 1 input, right? So only difference is this, right? So we have the output Y over there, right? So you can see that output Y is ended, right, from, right, see the complement of X, then we have A, and then we have B, right? Okay, so we can obtain the state equation, right? JA, KA, DB, right? So there is another difference, right? So that I should mention that over here we have D flip-flop, right? So let's start another example, right? So you can see the difference, right? So here we have 2 flip-flops, right? So before that example, what we did, we have the same flip-flops, right? If we have D, then we have D flip-flops in the circuitry, and if we have JK, we have all flip-flops JK, right? So there is a difference over here that we have the mixed different flip-flops, right? So here we have JK and D flip-flop, and here you can see that another difference is before this we have the output, right? So here we have the output, but before output we have the combinational logic AND gate, right? So you can see that the inverted signal from the input, right, and A, and then the output from this flip-flop, that is B, they are ANDed, and we have the output, right? So you can say that output has the combinational logic before, right, going to the Y, right? Okay, so what we can do, we can straight away have state equations that are written over there, right? So, and you can calculate or compute those state equations, right? So we have JA, right? So because this is the A, so KA, right? So this is the type of the flip-flop, right? So here you can imagine that why we are using two letters, right? So J mentioning the flip-flop, A is the tagging, right? So here we have D type of flip-flop, and this is the B, right? So this is the unique tagging for this flip-flop, mentioning that this is the flip-flop, right, B. And here we have X, right, and then we have Y, right? And after substitution, what we get, right, we get A. The next state is this, right? So these are the state equations, right? So you can see, right, we have the state equation. Then what is the next, right? So as we have two flip-flops, right, having two output A and B, right, and one input, so these are the combinations. Normally we mix the current state with the input, right, and then we have next state. So here you can see that we have next state with T plus 1, right, and this is the output. So what can be done, right? So you can see that we have we have to put those values, different possible combinations, right, in those state equations, right, and then we can get the next state, right? So this is the way out to populate this state table, right? And from this state table we all know that we can get the state diagram, right? And then we have another example, right? So here we have used the T flip-flops first time, right, regarding the sequential circuit analysis, right? We can see that we have two flip-flops, T flip-flops, right, and we have one output, one input, right? So same set of questions we have to answer. Yes, this is a sequential circuit because memory is involved, or we have the states, and right, and then we have the feedback. You can see that this is the feedback, and input, one output, right? So how many states we can have, right? So you can answer those questions or queries, right? And then as we normally review the flip-flop, so this is the characteristic table and the characteristic equation for this T flip-flop, right? So this is T, this is the next state, and this is the characteristic equation for this flip-flop, right? Okay, and then we have the state equations, right, and we have the next state, right? And after having those equations, what we can do, we know the possible combinations. We only have to put those values there, and then we can get the next state, right? So here you can see we have the next state and we have the output Y, right? So you can see that output is the right and operation between A and B, right? So you can see that whenever we have both 1 1, we have 1, right, 1 1 1, right? And here we have the states, right? So you can see the difference, right? So here we have 0 0, 0 1, 1 0, and 1 1, right? Right? So you can see we have mentioned the output, right, over there. So here what is something new, right? So you can see that the output, right, is dependent only on the current state, right? Okay, so here you can see that output is dependent on the state only, on the current state only, right? And this type of machine is a Mealy machine, right? So let's talk about the model or different type of machines, right? So we can have we have two type of finite state machines, right? First is Mealy machine, right? Mealy model, or the second one is Mealy model, right? So in the Mealy model, right, output depends on the current state and the input, right? And in the Mealy model, on the other side, output depends only on the current state, right? So you can see that we have in the previous example, output is dependent only on the current state or present state, right? So there is another feature of the Mealy machine is that output is not clocked, right? So we don't need any clock for the synchronization of the output, right? So this is not a sort of synchronous, right? Okay, and so we not need to mention the difference regarding the models, right? Or whenever we talk about the sequential circuits, so we sometimes we use the state diagram, and when we talk about the state diagram, we have to mention different states, and then we have different arrows, we have different inputs and outputs, right? So this is very logical that we can differentiate between the representation, right? And normally we have two type of different models, right, or state machines, and these are Mealy and Mealy, right? So we have the state diagram, right? So you can see that we have the state diagram mentioning different states, right? So here, if I tag, so this is the state, right, S1, and this is the state S0, right, and this is the output, right? In the denominator we have the output, in the numerator we have the state, right? And this transition is plotted or shown by this arrow, right? So here the cost of this transition is this input, right? So we have to apply 0, right, if we want to move from this state to this state, right? So you can see that output depends only on the current state, right? So this is the output, right? So there is no dependency of this output on the input, right? So you can say that in a Mealy machine, right, output is only dependent on the current state, right? And on the other hand, here we have the state diagram, right? You can see we have mentioned different states, S0, S1, S2, S3, right? And we have different values. So this is input, this is output, and this is the state, right? So here you can see that output is dependent. So because the output is here, right? So it is dependent on the current state and the type of input, right? Moreover, there is another very key difference, that the output is not synchronized with clock, right? So here we have the models, right, regarding the block diagram, right? So you can see that here we have Mealy machine, right, and here we have input. This is the combinational logic for the next state, right, and this is the combinational logic for the output, right, and this is the state register. That is, you can say these are the flip-flops, or the sequential part is here and the combinational part is here, right? And here you can see that we have input, right? So output, right? So if I go back, this is Mealy, right? So output is dependent on the current state and the input, right? Current state and the input. So you can see this input, right? And here there is no direct connection between the input and this output, or this combinational logic representing the output, right? So this is the next state combinational logic, registers in order to store the states, right? And here we have the combination logic for the output. So you can see that there is no connection, direct connection between input and the output, right? So over here we can see this line. So over here we don't have any direct connection, right? So it means output is dependent only on the current state, right? So if I go back, right, so here you can see this is the Mealy machine, and output is dependent only on the current state, right? Right. So here we have another representation, right? So you can see that we have flip-flop that is sandwiched between two combinational logics, right? So this is the logic for the, right, next state, right? And this is the combinational logic for the output, right? Right. So this is the sequential part, and this sequential part is used to store the states, or this is the memory, right? And again here you can see that this is Mealy machine, right? And you can see that there is connection from input, right, to the output combination logic, right? So here you can see that we have again combinational logic sandwiched, right? Flip-flop is sandwiched between two combinational logic, right? And here we have input, right? And there is no direct connection between input and the output, right? And if I talk about our textbook, right? So in our textbook, right, Mealy machine is highlighted, right? Right. But you can find the Mealy machine, but the main focus is on Mealy machine, right? Okay. So this is again comparison, right? So this is the name, Mealy machine or Mealy model is named after a scientist, right? And this is again Mealy model named after the scientist or its inventor, right? And usually specified on states, right? So output is specified on the states, output is usually specified on the transition, right? So you can have an idea, right? So these are the examples, right? So here we have Mealy and Mealy machine or Mealy state diagrams. We can always have transformation, right? So this is the transformation if you want, right? You can have Mealy model, right, with a Mealy machine, right? And again you can have a Mealy model with a Mealy machine, right? So you can transform. And here we have the tables, right, mentioning the different models, right? And again here you can see that we have mixed model over here, right? So you can see that here state 0 0, it is we have output within the state. So this is Mealy, right? So 0 1 0 1 and 1 0 1 0 and 1 1 Mealy, right? So we can always have the mixed model, right? So that's all for today's lecture, right? And today we have studied more sequential circuit analysis, right? And we talked about different state machine models, right? And we have compared Moore and Mealy state machine models, right? And then we have seen an example where we have used the mixed model, right? So it means we can have a state machine where we have the Mealy as well as the Moore model, right? And we have gone through different examples, right? So that's all for today's lecture, right? So I wish that you should solve more and more examples from your textbook, right, in order to have a full command or grip over this topic, right? So that's all. मेरी तरफ से आपको अल्लाह हाफ़िज़, अस्सलाम वालेकुम.